Hi everybody, I'm Tim,
I'm Mason.
and today we're going to show you the Sipser-Gacs Theorem in Chapter 7. So the Sipser-Gacs Theorem says that the class of languages BPP is a subset of the intersection of the class of languages sigma 2p and pi 2p. So earlier in the chapter, we defined what the class of languages in BPP are, and so a language is in BPP if there exists a deterministic Turing machine that runs on, so let's call this machine M, that runs on the input M R X, where or X R, where R is of size so R is an element of sigma to the M, where sigma is just our 0, 1, our language, or our alphabet is our so sigma is our alphabet, and sigma to the M, and M is some polynomial in terms of the size of X. So for every R in so you can think of R as just like a random string of that length, and then if you think of it like that, then L is in BPP if for this Turing machine the probability over all R's that M accepts, or that the result of MXR is equal to whether or not R is actually in the language. So what this is essentially saying is that if L is actually in the language, this should accept, and if X is not in the language, then M should not accept, M should reject. So if this probability that essentially gives the right answer is greater than or equal to 2/3 for all for all X. Now, there's a nice theorem in the book. I think it's theorem 7.10 that says that we can essentially just run this Turing machine over and over a polynomial number of times on itself, and that'll reduce the amount of error in this probability. So it'll actually reduce the error all the way down, so that the probability. So we can just assume that the probability that MXR accepts or gives the correct answer is greater or equal to 1 minus 2 to the negative size of X. So essentially what this means is it gives an exponentially small error given in terms of the size of our input. So it gets extremely close to the correct answer essentially, but there's still that probability of error. So, and recall that sigma 2p is a set of all languages, is the class of languages that can be determined by, or that have has the form where there exists as a polynomial Turing machine M prime, where there exists a U1 for all U2, the Turing machine will accept on X, U1, U2 right, so X is in our language if and only if this accepts for all U2 for some U1, essentially. And pi 2p is just the complement of sigma 2p. So if L is in sigma 2p, then L complement is in pi 2p. So we can show that BPP is closed under complements. So if L is in BPP, then L complement will also be in BPP, because we can just basically return the negation of our Turing machine, right? And that'll decide L complement. So that implies if we want to show that BPP is in sigma 2p intersect pi 2p, all we need to do is show that BPP is in either sigma 2p or pi 2p. So we're going to show that BPP is in sigma 2p. Okay. So recall that earlier we talked about how BPP, if a language is in BPP, then there exists a Turing machine that will take in x in a random variable and will almost always give the right answer. And so what we want to show is that we can translate this Turing machine into another Turing machine that, given that will be in this form and will always give the correct answer. So we can express the different values of R, right? So there's a finite number of different possible values. And they're all the strings of the form sigma to the m. So we're gonna just express these values as in this box here. So we're gonna say that any value in sigma to the m is inside this box, okay? And then we're going to we're gonna define a set Sx, right? And what Sx is Sx is the set of R's such that m of xr accepts. So if x is in L, then the set is going to be extremely large. It's going to be essentially the entire language, or the entire sigma to the m. So we're going to say this is what Sx is going to look like. It's going to be essentially all of sigma m. However, if x is not in L, then Sx is going to be actually really small. Right. So these are the only two possibilities. Either Sx is essentially all of sigma to the m, or Sx is only a small portion of sigma to the m. So what we want to do is we want to take our R, and instead of running our Turing machine on R, we're going to translate it in some way such that we're going to get more than one thing that we want to run our Turing machine on. And then, since we're running on multiple things, this could possibly expand this set Sx, right? So if we expand the size of Sx, it's possible that if this is the case, that it will then cover the entire set sigma to the m. But if the Sx is really, really small, then even if we expand it, if we make Sx a lot bigger, then there will still exist some points that are not in that are not accepted by the Turing machine, and these will be picked up by the universal quantifier. So the translation that we use is the exclusive OR operation, and we perform this on multiple vectors u. So we're going to let u be the set u1 to uk. We're going to let this be a subset of sigma m. And where k is equal to the ceiling of m over n plus 1. So essentially we're just picking k values in sigma to the m. That's essentially, and we're letting those be in the set u. So then we're going to take these values and we're going to exclusive OR them with our with our R. So remember, what exclusive OR means is that the bit a bit is 1 in the output if and only if the two corresponding bits if one of the two corresponding bits in the two inputs is 1. So for instance, if we have, let's say, 1, 0, 1, 0, and we exclusive OR that with a 0, 0, 1, 1, then we're going to get the value. So if we exclusive OR that, we get the value 1, 0, 0, 1. Okay. So we're going to perform this exclusive OR operation on all of our for R on all of our U values in U, and then we're going to run our Turing machine on that and output 1 if and only if one of these output 1. So essentially what we're going to be saying is that there will exist some U such that for all possible R's, if we perform this operation on every single one of these U's, and then we OR them all together, that's going to be 1 if and only if X is in our language. So we're going to, like I said, we're going to take the R over all the possible UK's, and we're going to run M. Our original M are not our probabilistic Turing machine. Or it's actually a deterministic Turing machine that just takes in a random variable. So we're going to run that on X and our exclusive ORed with our UI. And so if this is equal to 1, then our X is going to be in our language, and if it's not equal to 1, then our X is not going to be in our language. So basically, this expansion can only, you can see that there will only exist if S of X is really, really small. Then no matter how we expand it, no matter which vectors we pick to expand the size of our Sx, there will still be some values out, so we're going to expand it, but we won't expand it enough that there will still be some values that this will not equal 1 on. So then this part will fail of the universal of our expression here. But if X is in the language, then there will exist some of these vectors, and no matter which value we pick, it'll be in the expanded Sx. So if we run M on X and our exclusive ORed, our UI, one of those is going to output 1. And so when we OR them all together, it's going to output 1. And as you can see, this is in the form of a sigma 2p language. So that will imply that our L is going to be in sigma 2p.
So I'm going to give a more detailed run through with proof, and recall that what we're trying to show is that there exists some set U, which we can break down as U1 through UK, where the size of, or where K is just ceiling of M over N, such that for all R in sigma to the M, the OR over the K of M of R, exclusive OR with UI, X equals 1, and this is if and only if X is in L. So basically, if X is in L, then there's going to exist some set of vectors in sigma to the M, which we call U, and we can break this down as U1 through UK, and the size of this is just a K equals ceiling of M over N plus 1. Such that for all vectors in sigma to the M, when we shift R by one of these vectors, it will become an accepting vector, and so at least one of these K will lead the Turing machine M to accept. And so we have to handle two cases to prove this if and only if X is in L or if X is not in L. So first we'll handle the simpler one, which is case 1, X not in L. So remember from the diagram, this is sigma to the m. Here is our set of Sx. This is the random input strings for which the Turing machine M accepts. So it is very small. We know that the size of Sx is no more than the total number of these strings, 2 to the m, over 2 to the n, because the probability of error after our error reduction procedure, P of error, is less than or equal to 2 to the negative n. That's where this comes from. So we know this is very small relative to the size of all sigma to the n. So we can write this as 2 to the m minus n. Okay, so remember that the size of our set of random vectors that we can use is k, which is ceiling of m over n plus 1. So basically, we're going to take Sx, the set of all accepting input random strings, and exclusive OR it with every string in U. And so we take every string in this set and exclusive OR with every string in this set to produce a new set. And we can say that the size of this set is less than or equal to size of Sx times size of U. And that's because there may be collisions here. So otherwise it would be the size of the cross product, which is the product of these, but it's less than or equal to because some of these may be equal. And so we can say that this is equal to size of Sx, which is 2 to the m minus n, less than or equal to. And then we're multiplying by ceiling of m over n plus 1. And we can say that this is less than 2 to the m for a sufficiently large n. Okay? So we know that the set of sigma to the m has size 2 to the m, and the set of all, the size of the set that we can produce by exclusive ORing the accepting strings with u is less than 2 to the m. So therefore, there exists some u such that we cannot produce it here. So there is not any set of these offsets such that for all r is n union over k of Sx exclusive OR with uk. So this proves the first direction, case 1, for x not in L. And we still have to prove case 2, where x is in L. So just to reiterate, we want to show that for all x, or if x is in L, this language that's in BPP, we want to show that there exists some set of offset vectors in sigma to the m, where sigma is just 0, 1, and m is the length of the random input, such that for all r, sigma to the m, for at least one, this is OR, over these k offset vectors, our Turing machine is going to accept our input x on the exclusive OR of r and that ui. And so now we're going to handle the second case where x is in L. We want to show that if x is in L, then this must be true. Okay, so let's define a bad r, dr, to be any r in sigma to the m, such that this is not true. So this would be, we're trying to avoid the existence of these BRs so that we can find a U such that there isn't any bad R. So a bad R is where R is not included in the union over K of Sx exclusive ORed with UI. So basically Sx is the set of all random vectors in sigma to the m such that the Turing machine M accepts S comma Y, let's say, where Y is an Sx, and we're exclusive ORing with one of these UIs. So we want to show that for some U, no bad R exists. And we're going to use a probabilistic argument. Oh, R is not in UK. Okay, so R is bad if R is not contained in this union. So basically, what we want to show is that the probability that there exists a bad R, and we're taking this expectation over all U, where we're choosing the K u vectors at random is less than 1. So if this probability is less than 1, then that means that there must exist some u such that there isn't any bad r. Another way of saying that is that if you look at all of the possible u's, then not all of them leave any potential for there to exist bad r. Okay, so this would imply that there exists a u such that for all r is good. So we can bound this using the union bound. So the probability that there exists a bad r is less than or equal to the sum over all r of the probability over u that r is bad. And again, by bad, we simply mean that r is not contained in Sx exclusive ORed with ui, the union over all of the ui's. Okay, and the reason for this is because if there exists a bad r, then at least one or more of them is bad. And so the probability of there existing bad r is no more than the sum over the r of the probability that particular r is bad. Okay, so this is equal to the expectation of a particular r being bad times the number of r's. So we can say that this is, if this is less than 2 to the m, 2 to the negative m, so if the probability over randomly chosen r and u that r is bad is less than 2 to the negative m, then we have this. We have that the probability of there existing a bad r is less than 1. And the reason for that is that we can just take the sum over the 2 to the m possible values of r with something less than 2 to the negative m, and the result will be less than 1. So it would be sufficient for us to prove this. So we want to show that the probability over r and u that r is not contained in this is less than 2 to the m, 2 to the negative m. Okay, so first we want to observe a few properties of the exclusive OR operator. So let's say r is uniformly random in sigma to the m. That means that r is in sigma to the m, and any value of 0, 1 to the m is equally likely to be represented in r. And now let's say you exclusive OR r with some value u. Now this is also going to be uniformly distributed over sigma to the m. And the reason for that is just that the exclusive OR operator is 1 to 1. So if you take r exclusive OR a and exclusive OR with a again, you get r back. So essentially what you do when you take a uniform random value and exclusive OR it with something else is you're just permuting the possibilities of what the output of this random number could be, and still all possible outputs are equally likely. So more specifically, so we have r is chosen uniformly randomly, so r exclusive ORed with any given ui is also uniformly random. That is, it's equally likely to be any value in sigma to the m. And then over all these different ui's, assuming that we've chosen them uniformly randomly and independently, then these outputs are going to be IID, or independently and identically distributed. So that means that basically we can say that the probability that r exclusive ORed with a given ui is not in Sx is less than or equal to 2 to the negative n. So let's see why this is true. We've assumed that x is in L, and so we know by the error reduction argument that the probability of a given x not being accepting, not being in Sx, if you choose it at random, is less than or equal to 2 to the negative n, where n is the size of x. So this is chosen uniformly at random, therefore the probability it's not in Sx is less than or equal to 2 to the negative n. So the probability that r exclusive ORed with u, any of the u's, none of them is in Sx, we can just take the product. It's less than or equal to 2 to the negative n multiplied by the size of u, which is just ceiling of m over n plus 1. And so the n's basically cancel, and we have the plus 1, so this is going to be strictly less than 2 to the negative n. So basically what we have is the probability that R, exclusive ORed with one of these ui's, is not accepting, is less than 2 to the negative n. And how many r's are there? There are 2 to the m of them. And so, as we argued before, this proves that the probability over u that there exists a bad r is less than 1. And that means that there must exist some set of these ui's such that for all r is not bad, which just means that for one of these k, one of these ui's, m is going to accept on r exclusive ORed with that vector u as the random input and x. So this proves our claim. And then just for good measure, we can say that this is in sigma 2p because, or at least the polynomials work out because we have polynomially many of these ui because k is just ceiling of m over n plus 1. And we remember that m is polynomial in n, so each of them is polynomial in size, so the union of them is polynomial in size. This is polynomial in size, and we have only polynomially many of these ORed together outputs, and so this can run in polynomial time. So therefore, if x is in L, then we have this condition. And we already showed that if x is not in L, then this is not true. So x is in L if and only if this is true. And therefore, BPP is in sigma 2p. Finally, just to wrap up, we have to show that if L is in BPP, then L is in the intersection of sigma 2p and pi 2p. So we've already shown that if L is in BPP, then L is in sigma 2p. So we know BPP is closed under complement. This means that if L is in BPP, then the complement of L, L bar, is also in BPP. This is fairly intuitive. Basically, if a deterministic Turing machine with random inputs accepts x and gets the correct answer at least 2/3 of the time, then for the complement, it can simply flip the result and it'll still be correct 2/3 of the time. So if L is in BPP, L bar is also in BPP, and that implies that L bar is in sigma 2p by what we've proven earlier. And then by the definition of pi 2p, if L bar is in sigma 2p, then L is in pi 2p. So based on what we've already proven, we can see that if L is in BPP, then L is in pi 2p. So therefore, BPP is a subset or equal to sigma 2p intersect pi 2p. And that's it.